Good day, students. On this clip, we're going to be going over the principles of mathematical induction. We're going to be looking at two examples. So let's write down the title of this lesson: Principle, Principle of Mathematical Induction. Mathematical Induction. All right. So let's start out by taking a look at example number one. Prove that the statement s of n, which is 2 plus 2 squared plus 2 to the third plus dot 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 plus 2 to the n equals 2 times 2 to the n minus 1. The statement is true for n greater than or equal to 1, or all positive integral values of n. Okay, prove that this is true. Alright, so to do this, we're going to start out with the base case. So for the base case, what we're going to show here basically is that we're going to show, we need to show that, uh, true for n equals 1. Show that the statement is true for n equals 1. Okay? So that's the first, that is the smallest positive integer, 1. So that's what we'll start from n equals 1. So we're going to show that s1 is true. That's the goal here. We want to show that s1 is true. So to do that, we need to plug in 1 and see if we can arrive at an equality when we substitute 1 for n on these two sides. So for the left side, I'll plug in 1, 2 to the 1, and on the right side, I'm going to plug in 1 also. 2 to the 1 minus 1. I arrived at this by plugging in 1 here and then plugging in 1 there. Alright, so if we arrive at an inequality, our base case holds and we can advance. Alright, so 2 to 1 is just 2, equals 2. 2 to the 1 is 2 minus 1 is 1. Is 2 equal to? Yes, it checks out, so our base case is true. So we have a solid foundation, or a solid base. Now we're going to move on to the two-part step, which is the inductive step. Two-part inductive step. Okay? So the inductive step is comprised of two parts. So in the inductive step, we need to show that uh, true for n by assumption, true for n by assumption follows true for the next step, which is n plus 1. Follows true for n plus 1. So this is the main goal of the inductive step, okay? So in the first part, we need to make an assumption. The assumption is known as the inductive hypothesis. Inductive hypothesis, okay? So inductive hypothesis part, what we're going to do is we're just going to assume that for any arbitrary n value, the statement is true. So assume true for n. Okay? Assume true for n, so we basically need to show that Sn is true. That's the goal right here. So how do we write that down? All we just simply do is we just rewrite the original question and assume that it's true. So Sn plus 1 is true. We're going to assume that um, 2 plus 2 to the second plus 2 to the third plus dot 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 plus 2 to the n is equal to 2 times 2 to the n minus 1. We're going to assume that this statement is true for n greater than or equal to 1. We are assuming that is true. Okay? That's what the inductive hypothesis is all about. We're making a hypothesis that the statement is true for n. Now the proof, which is the challenging part, for the proof, we need to show that if this assumption follows that the next step is true, then we're done, because that means that the pattern continues like a domino effect. It continues forever. So for the proof, we must show we must show we must show the assumption, this assumption right here, the assumption follows that n plus 1, which is the next step, is true. Okay, if we can show this, rewrite this, if we can show that the assumption follows that n plus 1 is true, then we're done. Okay, so in this case, the task is to show that Sn plus 1 is true. Okay, based on this assumption right here. So if we can accomplish this goal, then we're good. All right, so what we're going to do is let's start by writing down what Sn plus 1 is. So Sn plus 1 is basically Sn plus 2 to the third plus dot 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 plus 2 to the n. Okay, my dot's supposed to be lower, so plus dot 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 plus 2 to the n. This is just what I wrote here, okay? And then I'm going to take the next step. The next step is what you get when you replace n with 2 to the n plus 1. So plus 2 instead of n, the next step, we're going to take one step up, since we're going by integers, 2 to the n plus 1, okay? And on the right side, just write down 2. Anyway, you have n, just replace it with n plus 1. N plus 1, because the last, see this variable here? N, that's what goes here, right? So we have n plus 1, that's what goes for n on the right side. Alright? So there you have the state Sn plus 1 statement. If I can show that this is an accurate inequality based on this assumption, then I'm done. Okay? So first of all, we're going to start by making a substitution. You see, if I take a look at if I take a look at the first part of my of my of Sn plus 1, this statement right here, let me box it so you can see. If I take a look at this piece right here, that piece is equal to something else. See this piece right here? What is it equal to? This piece right here. This one, this piece that I have circled, is exactly the same as this equation right here. But since based on our inductive hypothesis, since this is equal to that, I can simply replace that with this expression right here. Okay, so I'm going to make that substitution. Okay, so this whole piece right here, I'm going to substitute with what I said it is equal to on my inductive hypothesis, which is 2 times 2n plus 1. So I'm going to replace it with 2 times 2 to the n minus 1. I got that from my inductive hypothesis. Okay, that plus 2 to the n plus 1. And then let me start simplifying the right side while we're at it. Alright, so I'm going to have 2 times 2 to the n. Let me just write it as 2 times, let me write it as 2 to the n times 2 minus 1, like that. Alright, so in this case, I'm going to distribute this 2 to both sides. So I'm going to have 2 times 2 to the n minus 2 plus 2 to the n times 2 equals, now I can distribute this 2. It's going to become 4 times 2 to the n, because I multiply this 2 by that 2, and I use the commutative property of multiplication to switch it around, minus 2. Okay? Alright, now let's take a look at this side right here. I can write this as 2 times 2 to the n, and I move this to the front, collect like terms, 2 times 2 to the n. Because these two is they are a product, right, and multiplication commute, so I can switch this order around. Minus 2 equals 4 times 2 to the n minus 2. Okay? Now, if you look on this side right here, I can factor out 2 to the n, or I can factor out 2. So let me factor out 2 to the n. So I'll factor out 2 to the n and 2 to the n. Factor it out 2 to the n, I'll be left with 2 plus 2 minus 2. 4 equals 4 times 2 to the n minus 2. What is 2 plus 2? 2 plus 2 is 4, so I'm going to have 2 to the n times 4 minus 2 equals 4 times 2 to the n minus 2. Using the commutative property of equality, I can switch this around. This is basically the same thing as 4 times 2 to the n minus 2 equals 4 times 2 to the n minus 2, which shows that it's true. All right, so since, writing a concluding remark, since true for n follows true for n plus 1, the original statement, Sn is true for n greater than or equal to 1. This is the same thing as all positive integers. Okay? So there you have it. All right, let's go ahead and move on to example number 2. Number 2, we're going to try and prove that. Um, all right, so I want to prove that prove that 5. Let me change my pen to this one. Prove that 5 to the n minus 2 to the n is divisible by 3 for all positive integers. Okay, so that's what I want to prove. So this is written in English form. I like to translate the statement into mathematical form so I can use my formulas to work this out. All right, so how can I write this statement in Sn form? So this statement is what we're basically trying to prove is that I want to prove that a statement Sn, the statement Sn, which is that 5 to the n minus 2 to the n is divisible by 3, basically means that this expression can be written as a multiple of 3, which is 3k, for some integer k, and n is greater than or equal to 1, since we're working with positive integer values. Alright? So that's a statement that we're going to focus our attention on, this statement right here, okay? Alright, so let's start with the base case. Alright, the base case. So for the base case, what we're going to be doing here is we want to show that the statement is true. We want to show true for n equals 1. Okay? I want to show that this is true. So basically, we're going to do S1. If I plug in 1 for n in this equation, on this side of the expression of the equation, do I end up with a multiple of 3? That's the question we're asking ourselves. So I'm going to rewrite this using 1 as my substitute for n. So I'm going to write 5 to the 1 minus 2 to the 1. Is it equal to a multiple of 3? Is it? So 5 to the 1 is just 5. 5 minus 2. Is it a multiple of 3? 5 minus 2 is 3, right? Can I write 3 as a multiple of 3? Absolutely. If I divide both sides by 3, I'll see that k is 1. So I can write this as 3 times 1 equals 3 times k. So you can see here that k is basically, k is 1, right? So I can rewrite this as 3 times 1 equals 3 times 1. That shows that my base case is true. We have a solid foundation. My base case is excellent. Alright, now that I have the base case, we're going to move on to the inductive step. The inductive step. This is a two-part component, the inductive step. So for the inductive step, here, what we want to do, let me underline it first. For the inductive step, we want to show that true for n true for n follows true uh, for n plus 1. Okay, so true for n, this is by assumption. If we assume true for n by assumption, it follows that n plus 1 is also true. Okay? Alright, there are two parts. We're going to start with the inductive hypothesis. Inductive hypothesis. Alright, that's the first part of the inductive step. So for the inductive hypothesis, we're going to start with an assumption. Okay, so we're going to assume, um, we're going to assume, assume uh, true for n. Okay, we're gonna assume that the statement is true for n. So we need to show that we need to just state that Sn is true. Okay, Sn is true. So how do we do that? I'll just simply rewrite assume that the original statement, this is the original question right here, just assume that that's true. So we're gonna assume that assume that uh, um, 5 to the n minus 2 to the n is equal to 3k for some, oh, it's sorry, it's true. Assume that this one is true, for some integer k, and n is greater than or equal to 1, or is a positive integer. Okay, so assume that that's true. Now the next part is the proof. The proof. For the proof, we want to show that so for the proof, we must show that the assumption, this assumption I made here, the assumption follows that n plus 1 is also true. Okay, so if you can do this, then we are done. All right, so let's do this. What is that going to look like, this component right here? We want to just basically show that this statement follows that Sn plus 1 is true. So if we can show that Sn plus 1 is true, we're done, because the pattern will keep having that domino effect of going on and on forever. Okay, so let's rewrite Sn plus 1. So what will Sn plus 1 look like? We're going to write 5 to the n plus 1 minus 2 to the n plus 1 equals 3 to the r. You need to use a different variable here since k is already taken. Is for some integer. Oh, it's not. Okay. For some integer r, and you know what the business is with n, right? N is bigger than or equal to 1. All right. So now we have this. Okay, we need to show that this is true. If we can show that this is true using this somewhere in our whole process, then we're done. Okay. So let's start by using a law of exponents to break down this powers right here. So this is basically going to become 5. This is a different pen. It's going to become 5 to the n times 5 to the first power minus, let me rewrite the order. Sorry about this. Let me rewrite it as 5 times 5 to the 5 times 5 to the n. So write it as 5 times 5 to the n. This is 5 to the 1 times 5 minus 2 times 2 to the 1 times 2 to the n equals 3r. Okay? So if we take a look at this, what I did basically is I just broke down these powers because n 5 to the n plus 1 is just the same thing as 5 to the 1 times 5 to the n, and 2 to the n plus 1 is the same thing as 2 to the 1 times 2 to the n. Because when you're multiplying exponents, what do you do with the powers? You just simply add the powers, okay? So now we're going to use that technique I showed you earlier. We're going to take a look at the first number and the last one, and then think of multiples of the first and the last that add or subtract to give you the middle number right here, which is 2. Okay? So let's make our chart on the left side. And then we have 5 and 3. What are some multiples of 5? 5 times 1, 5. 5 times 2, 10. 5 times 3, 15. 5 times 4, 20. 5 times 5, 25. Let's stop there. 3 times 1, 3. 3 times 2, 6. 3, 3, 9. 3, 4, 12. 3, 5, 15, and on and on. Okay? So, let's see. Any combination that can add or subtract to give you the middle number, which is 2. Oh, wow. Check this out. The first one works, which is nice. 20 and 18 also work, but that's good enough. Let's just use 5 and 3. Okay, if you use 20 and 18, that'll work too. So we're going to use this first pair that happens to work out for us. Okay, all right, so let's do it. So I'm going to rewrite this as 5 to the 1. I don't need to put the 1 there anymore, huh? So just 5 uh, 5 times 5 to the n. Remember, the goal is to replace this middle one, right? So minus, instead of 2, I will replace 2 with 5 minus 3, because I didn't change the equation. 5 minus 3 is 2, times 2 to the n equals 3 to the r. Alright, now, let's see. If I simplify, I'm going to have 5 minus 5, 5 times 5 to the n minus 5 plus 3. Made another mistake. If you look here, you have this 2 to the n over here, so we're going to distribute this 2 to the n to the first term, and we're going to also distribute it to this one right here, okay? So when I distribute it, I'm going to have 5 times 2 to the n, and then this minus and that minus makes it a plus, and then distributed to that, you have 3 times 2 to the n equals 3 to the r. Sorry about that. Alright, now let's take a look at the first two. Can I factor out something from the first two? 5 and 5 are common, right? So I'll extract the 5 from the first two, and I'll be left with 5 to the n minus 2 to the n plus 3 times 2 to the n equals 3r. Okay? Now take a look at this. 5 to the n minus 2 to the n. Does that look familiar? Anywhere? Absolutely. Check this out. 5 to the n times 2 to the n is equal to 3k by our inductive hypothesis. So we can make that substitution right here. So I can rewrite this as 5 times, instead of this, based on my inductive hypothesis, I can make that 3k. Okay? And then plus 3 times 2 to the n equals 3r. If I multiply these two, I'm going to have 15k plus 3 times 2 to the n equals 3r. Now, can I factor out 3 from these two? Is 3 a multiple of 5? Absolutely, and clearly 3 is a multiple of this expression here, because you can see it's 3 times something, okay? So I'll factor out a 3, and I'll be left with 5k plus 2 to the n equals 3r. Alright, if I divide both sides by 3, we can clearly see that r is equal to 5 to the k plus 2 to the n. Okay, if I divide these two by 3, you see that this is equal to that. Okay, so let's make the obvious substitution, and we can wrap this up. We can just say that 3 to the r is equal to 3 to the r, which shows the inductive hypothesis, which shows our proof is correct, and then we're good. So let's write down our concluding remark. Since true for n follows that n plus 1 is true, then our original statement is true for n greater than or equal to 1. Okay? So thanks for paying attention to this presentation. Um, and if you want to get more updates, do subscribe to my videos, okay?